Hi and welcome to Unit 1, Topic 3, Video 3. And in this video, following on from our direct proof video, we're talking about proof by contrapositive. Now, let's be honest, proof by contrapositive is probably the one that people find the most tricky. It's a little bit different to what we normally play with. It's theoretically challenging to think about, but procedurally it's quite easy. And then it does involve using a direct proof and creating a simpler situation in a proof that might otherwise be quite hard. Now, the first thing that you need to know and be aware of is the negated statement. So if we're asked to use the negated statement, it means we're being asked to use the exact opposite statement. So let's talk about not P, because we've got to be a little bit careful. I.e., let's say we're talking about 5 is odd. Well, if 5 is odd, then the not P, the negated statement, is probably easier said as 5 is not odd. But we know that fortunately we can use the concept that if 5 is odd, then the negated is 5 is even. So that would be fine. But the only problem with 5 is even is, where do we define 0? Is 0 odd or even? And so do we actually have, does even and odd count every number? But that's why we probably stick with that one there. There are 3 people in the room. So the negated statement to there are 3 people in the room is there are not 3 people in the room. It's basically anything but the statement that's made in the room. So you couldn't say there were 4, 5, 6, 7, 8, 2, 1, 0, and then go off to infinity, because we don't have time for that. So we'd have to use a not statement here for sure. That should probably say body or everyone. Everybody enjoys tennis is the statement. And the negated statement for this, is not, so this is the tricky bit here, is if you've got everybody here and you're saying they all enjoy tennis, well, let's say there's 100 people here and 99 of them enjoy tennis and one of them doesn't. Well, that then doesn't work. So everybody enjoys tennis can be negated by saying at least one person does not enjoy tennis. As opposed to the more commonly thought negated statement, which is everybody doesn't enjoy tennis. But then there's all this blurry area in between, because maybe some people do and some people don't. So there's your negated statement there, and that's probably the most important one. Every odd number is a factor of 99. It's the last one I want to talk about. And every odd number is a factor of 99 has a negated statement that at least one odd number is not a factor of 99. Or you could even counter this one, not that you're trying to prove it, but this would be a good counterexample proof. So this is an at least one odd is not a factor. Sorry for my rushed writing, but I know you didn't come here to watch me write stuff down. So these last two are really important, because you don't just swap it over and say not every odd number, or every odd number is not a factor of 99. You have to say, well, as long as one of them is not, then this is a negative statement. Now let's talk about De Morgan's law. This is what it's called, but you probably won't see that language used all that much. So De Morgan's law is that not P and Q and not P or not Q are the same. So let's have a look at this Venn diagram first of all. P and Q is the green bit. That's P and Q. And what's the same as the green bit? Well, the same as the green bit is the not pink, red, or orange. So green is equivalent to not pink, red, or orange. And then for the same reason, we've got the not P and Q is pink, red, and orange. And that's the same as not P or not Q. And green is the only one that fails that test, because it's both P and Q. So not P and Q is pink, red, and orange. And also not P or not Q is also pink, red, or orange. And then the other one is not P or Q. So P or Q is red, orange, or green. And therefore not P or Q is pink, is the same as not P and not Q. Not P and not Q is also pink. So it's worth taking some time to think about that, but it's basically our way of expanding a negated statement. And it might come in, it might be important. Now, I'm not saying you need to memorize De Morgan's law. It's not on your formula sheet, but it can be done logically, particularly if you think about a Venn diagram like this, and colors are often a nice way of looking at it. So, proof by contrapositive. We're going to go through the theory in this video very quickly now, and then we'll run through some examples in a later video. So, to prove the statement P implies Q, we can use the contrapositive that not Q implies not P. So what we're doing here is we are swapping the implication, and we're also negating both statements. And be careful with how you negate statements. So consider this one. P is I am in the pool, and Q is I am wet. Now we know this is true. P, well, I'm sure somebody will come up with a counter example like, you know, I'm inside a glass bubble or something like that. But let's assume I'm in the pool means I'm wet. So P implies Q. Being in the pool implies that you're wet. Does not Q imply not P? So if I am not wet, does that imply I'm not in the pool? And the logic would say, yeah. So the opposite of the implied thing is true. Well, then the implicator, which is P in this case, also must not be true. And it's worth some time now. We're going to finish the video in a second. It's worth some time now. Invest that time now. Just stop and think about that, because it does make sense, but it is a little bit tricky to get your head around. So that is the end of video 3. All the best.